last topic, which was asymmetric cross sections. And then we'll start talking about circular beams. So going a little bit out of order in the schedule. Last time we did this example looking at this unsymmetric cross section, which is just an angle section, and found the product moment of inertia for that section. And then knowing that with the other geometric properties, we could calculate the location of the neutral axis with respect to the YZ axes. And then calculate also the maximum tensile and compressive stresses on the cross section. So any questions? I know we kind of got to that point in a little bit of a rush. So any questions on that process or that example? Okay. All right, so then the last bit would be to plot these stresses on a sketch of the cross section. And since we have bending about both Y and Z, we're going to have essentially a three-dimensional sketch, or I'll show you how to break it down into different two-dimensional sketches, which is totally fine. What I've been doing in the last couple semesters is in your homework, when you have a problem like this, potential for extra credit if you do a very nice 3D sketch of the stresses, but it's not required. So for this problem, we calculated 3.52 in compression at point A, which was the corner, the outside corner there. And then the maximum tension was 4.13 KSI at point D, down at the bottom right. So what that would look like on a 3D sketch, something like this, where the neutral axis, so this is one key to the sketch, the neutral axis is going to cross the material where the stress is 0, That's important. And then you just have the arrows representing the directions, and then you've got the compression over here and the tension over here. Now, so I'll just note, this is your compression side, and this is your tension side. So if you don't want to deal with the three-dimensional sketch, it's totally fine in my book to provide two separate plane views of the stress distribution. So these would specifically be in the YX plane and in the ZX plane. So it would look something like, ZX. So the ZX plane is showing this part, and then the YX plane is showing this part, Where X, again, represents the direction of the longitudinal axis, also the direction of the action of the stresses, Positive or negative. So if you wanted to map this a little bit more to the 3D sketch, or you could just note your neutral axis is coming something like that on that one, and then it would be something like that over here. Any questions? Okay. Yeah, did you have a question?
Oh.
All right, fair enough. All right, so that wraps up the unsymmetric cross-section lecture. Already covered shear center through the lecture that was recorded, or lecture videos that were recorded, so you can catch those if you haven't yet. Goes through an example, so the shorter recording is the the longer example with the more complicated cross-section, that one there. And so this puts us back on track. Now we are going to talk about circular beams. And remember, I mentioned this as a highlight of the class when I introduced the class at the beginning of the semester. We are talking about beams that have circular axis. So they are curved about the axis with a constant radius of curvature. We're not talking about beams with a circular cross-section. So something like this, curved wide flange I-beam, or here's another I-beam with a 14-foot 10-inch radius. And then here's an example in application, right, a barrel vault roof at this performance center. I'm not going to try to pronounce it. So I think that's in Chicago, maybe. I don't remember. But anyway, these are the kinds of things that we're going to be talking about today. And then we'll continue with circular beam concepts later on. So after today, right, next week, we'll talk about strain energy in beams and Castigliano's energy theorem. So that will be just general stuff, not necessarily specific to circular beams. But then we will apply the Castigliano's energy theorem specifically to circular beams. We'll look at determinate and indeterminate conditions there. And then after that, we'll have exam 2, which will cover everything through today's lecture. Yes. Thank you. Yeah. No? Okay. There we go. All right. So after today, right, we'll talk about strain energy in beams, Castigliano's energy method. Then we'll come back to circular beams using Castigliano's modified energy method to calculate deflections for determinate and indeterminate beams. Then exam 2 will be a week from next Wednesday. Content on exam 2 will be through the current today's lecture, circular beams. Most likely. I may adjust that. I may bump the circular beam lecture to the next exam. We'll see how things play out with the homework assignment. And then after that, we'll start talking about torsion and then get into some more interesting topics like failure theories. So that's what's coming up. All right.
Kind of off topic.
Sure.
What would you call a beam that like curves to like the side? Like you see the bridges that like bend. Is that just like a curved beam?
Yeah. So so you're talking about a beam that is curved so that it's the axis is curved about it's curved about the other axis, right? Yeah. Compared to what we're talking about. Yeah. So that is just kind of a curved beam. I think it's probably more common than the stuff that we're looking at here with the curved axis beam, but that wouldn't affect. So it would be you'd have to treat it carefully in your analysis, but it wouldn't because the axis of bending isn't curved. It's not going to apply to what we're talking about today. But I would have just called those curved beams myself. Okay. So yeah, both can be called curved beams. It's just context. Yeah. Yeah.
What if it's got a circular cross-section?
And it's curved, a circular cross-section and it's curved, then I would call it a beam with a circular cross-section that is curved. Yeah, so we're going to set this up. So, we're going to be looking at this generic cross-section shape, right? Whatever you'd call that. But the equations that we're going to derive relate to beam bending, and they will be applicable to any cross-section, any generic cross-section shape. Yeah. Yeah, good questions. All right. Alrighty, so, staring at the wrong set of notes. I forgot to skip the shear center in my written notes. There we go. Circular beams. All right, so again, we are referring to beams that are curved along their axis or along their length, the axis of bending with a circular radius of curvature. So that's the best way to write that. Beams that are curved along their length with respect to the axis of bending. With a constant radius of curvature. All right, so first we'll outline the general assumptions that we are going to make for this process. We are assuming that the beam cross-section is symmetric about the y-axis. So I guess that modifies my earlier statement that this applies to any cross-section shape, not just any cross-section shape that's symmetric about the y-axis. And of course, the curvature is circular versus elliptical. We'll assume that the material is isotropic, homogeneous, and elastic. And we will assume that plane sections remain plane. All right, so I'm going to break down this image here and add a few sketches or notes to it. So what we're looking at is, all right, a representation of a small segment of length along a curved beam. So this portion of the figure is looking at the XY plane, right? So here would be your X direction along the axis, and then the Y is shown here, positive towards the center of curvature. All right, and then this is showing the cross-section plane. So that would be your that's your Y direction, and then Z direction. So here, really, the X is coming out of the page, just in that portion. Here, it would be your X, Y. So I'll sketch that on there. So we'll say, I'm going to place it at the neutral axis to be consistent with how we do things. So X there, and then Y towards the center of curvature. Here, we'd be looking at your Y, Z plane. All right, so this is the cross section. All right, so I'm going to start by just identifying or defining some of the things noted on here. So first, let's look at this capital R. capital R represents the radius from the center of curvature to the centroidal axis. All right, so that's the axis that passes through the geometric centroid of the cross-section. And normally, we have the neutral axis at the same location, right? The neutral axis normally passes through the centroid. In a circular curved beam like this, that is not the case. The neutral axis will not pass through the centroid. So we're defining Rn, this little guy here, lowercase r sub n, as the radius to the neutral axis before loading. So that's another complication. After there's loading applied to the beam, things are going to change. And then we also have rho. Rho is the radius to the neutral axis after loading. And you'll notice that rho is measured from a different point, a different center of curvature than capital R and Rn. All right, so I'm going to note that on here. This point is the center of curvature before loading. And then this point over here, I'll use a different color, green. That's the center of curvature after a moment M is applied. All right, so you can imagine if you have a beam that is pre-bent about its bending axis, right, pre-curved, then if you apply a moment in either direction, that's going to change the curvature of the beam, right? So it's going to change the point, the center of curvature, it's going to change the neutral axis location, and it's going to cause a lot of things to be weird compared to our usual calculations for straight axis beams. So say rho is radius to the neutral axis. After loading by moment M. Which rotates the cross section. And on the sketch, I have that notated as d theta is the change in curvature here. All right, so d phi is the original curvature, and d theta is the change. All right, so there's a few more items to define on this list. We have lowercase r without a subscript. This is the variable radius to an arbitrary line within the beam. And I've sketched an arbitrary line EF down here. So we'll use that as our reference for this definition. So the key thing to remember is that this is a variable radius. All the others are not variable except that rho will depend on the moment M. but they're not going to be, the others aren't going to be variable in the equations. Okay. All right, and then last but not least, I have this e, lowercase e, defined as the distance, radial distance between the centroidal radius and the unloaded neutral axis radius. So capital R minus Rn is E. All right, so I think I've got everything noted on here so far that I need. All right, so a few other notes, right? We've got the XYZ origin at the neutral axis, so that's consistent with how I drew those on there. And of course, bending occurs about the neutral axis. All right, so now we need to define the relationship between strain and loading, right? Or strain and, loading is what we're ultimately going to get to. Strain and stress first. So in order to do that, we're going to consider this arbitrary line EF, all right? And I'm going to say that the length of EF, represented by this term here, before loading, will be equal to R, which is, right, that variable radius to arbitrary line EF within the cross-section, times the original curvature of the beam, d phi. And that's going to be equal to substituting in, right, this relationship for, I'm skipping a step here. All right. So recognizing then that lowercase r, right, is also dependent on variable y. So y is the variable distance measured from the neutral axis, right, to a point, an arbitrary point within the beam. So y and r are closely related to each other. It's just that one is measured from the neutral axis towards the center of curvature, and the other is measured from the center of curvature towards the point where you're evaluating things within the beam, right? So we'll say r is equal to Rn minus y, and then substituting this relationship for Rn, we can write capital R minus E minus Y for lowercase r. So I'll note down here also that R is equal to Rn minus Y. And that's also how we got there. So after load is applied, we will define the amount by which this line EF has lengthened. So looking at our sketch, all right, this gray line here, right, this gray line represents the undisplaced position of the right face of this beam segment before loading, right? After loading, we have the new center of curvature. This line that aligns with rho represents the new position of that right face of the beam, right? So it's going to change position like that. So that small distance right there, I should really make this zoomed in even more for the handout purposes. We'll call that point F prime. All right, so F is this point here, the original position of that face on line EF, and F prime is the displaced position. So FF prime represents the lengthening of that line. And it would be lengthening for a positive moment, right? It would be shortening for a negative moment. But also, it would only be lengthening if you are in the positive y direction from the neutral axis, right? If you're in the negative y direction, it would be shortening for a positive moment. But in this case, where we've placed EF, it would be lengthening. So FF prime is equal to y d theta. And here I'll note that it is a stretch in this case because it lengthens when EF is below the neutral axis. All right, so that's positive y for a positive moment. Yeah, go. Question?
Yeah. Or the assumption plane section remains plane means that the cross section is not deforming in its dimensions, or is that what we're saying this is doing?
So saying plane sections remain plane, so that is basically saying that there's not going to be any horizontal slip between planes within the material. So right, any plane that you cut will stay in position relative to the other planes. Like if you divide it up like this, right, you won't have separation.
Yeah.
Yeah.
So the cross section will be deforming, and that's what we're saying.
Well,
As in-
no. So the cross section itself. Let's see. So it's going to be, the deformation will occur longitudinally. Yeah. It's not, so the cross section itself won't be deforming. Yeah. But yeah, so you'll see, right, it'll compress there and it'll lengthen there.
Right.
Yeah. All right, so now we'll think about the axial strain. All right, so this is going to occur, right? The axial direction is now curved, right? So it's essentially, since we're dealing with circular curvature specifically, it's going to be a circumferential axial strain. And so that we can begin by defining it as FF prime divided by EF, right? So that's the change in length divided by the original length. And so substituting in our definitions from previous page, we have y d theta for FF prime, and then for EF, we have plugging in Rn minus y for here, a little bit more convenient form, times d phi. And what this translates to is a nonlinear strain distribution with the depth of the cross section. So if we were to sketch in the YZ plane, right, your neutral axis, something like that, with a moment acting, your strain will vary something like this. right? So above the neutral axis, you would have compression, so negative strain or shortening, and below the neutral axis, you would have lengthening. So that's for a positive moment. And I'll also note on here, this is the positive y direction. So we'll note that strain does not vary linearly with y. And the stress distribution will be similar.
Which way is the z-axis pointing? To the left?
Yeah, the neutral axis would be with z to the left. Yeah. So. All right, so since the neutral axis does not change length with loading, right, that's the definition, that's built into the definition of the neutral axis, we can say that Rn, right, which is, hold on, I'm getting ahead of myself. All right, so Rn times d phi, we said, was the length before loading, right? So that's equal to rho times d phi minus d theta, which is the length after loading at the neutral axis. Let's see. Let's say, call this side, this is the neutral axis length after loading. And then this is the neutral axis length before loading. Now, if we go through and divide everything by d theta, then we can say Rn is equal to rho times 1 minus d theta over d phi. Or rho is equal to d theta over d phi. Sorry, I'm misplaced that equal sign. All right, rho times d theta d phi is equal to rho minus Rn.
Wouldn't, when we divide d theta over, we would have d theta over d phi minus 1?
Let's see, so Rn rho times d phi d theta.
Flip the,
Yeah, so let me see. Rho. And then that is also rho.
I think you just flip the,
Trying to remember what I did.
over d rho over d theta, or d phi. Oh, because you take the inverse instead of
So Rn, yeah, so let me think about that. Yeah, so this would be a 1, you're right, so I think I'm not showing all the steps to get there. So it would be 1 minus, or whatever, d phi d theta minus 1. But then we're moving this over to isolate Rn, so that would switch the position, yeah. Yeah. Fair question. All right, so rho minus Rn, just to make sure that I transcribed everything correctly here. Rho d theta d phi, rho minus Rn. Yep, okay. So we can say d theta over d phi is equal to 1 minus Rn over rho, which is equal to Rn times, in parentheses, 1 over Rn minus 1 over rho. And this all has a purpose, I promise. It's gonna... All right, so what that means is our normal strain is equal to Rn times y over Rn minus y times, in parentheses, 1 over Rn minus 1 over rho. All right, so pulling this for our normal strain, we got the y over Rn minus y, and then our definition for d theta d phi. Plug it in to get us that Rn and then this guy. So that is the expression for normal strain, right, distribution along a cross section. So that will get you this curve. This is also applicable to any beam in general, right? So if you think about a straight beam application, consider the mathematical limit of this equation as Rn approaches infinity, right? So Rn is that radius to the neutral axis from the unloaded center of curvature. So as that approaches infinity, that would represent a straight beam condition. The limit would be, if you plug infinity in there, you would get negative y over rho, and that's what we have from our straight beam normal strain derivations from before, right? All right, so that's just a quick check to map it back and say, oh, does this work for all conditions? Yes. But we're going to be focusing on this more complicated equation for the rest of this lecture. So now we want to relate stress and bring that into our equation. So if we ignore the stress associated with the transverse loading that may be present, then we just have normal stress in the longitudinal direction is equal to Young's modulus times normal strain. All right, business as usual so far. But now we start plugging in our new terms for normal strain, and we have capital E times y times Rn in the numerator, and then Rn minus y in the denominator. And that all gets multiplied by 1 over Rn minus 1 over rho, or capital E y over r times d theta over d phi. So we can say normal stress in X is equal to capital E times Rn over variable r minus 1 times d theta over d phi. And this is where y, right, we made a substitution to get there. So that's y is equal to Rn minus r. All right, and remember that both y and lowercase r are variables. All right, so this is the distribution of bending stress over the beam cross-section. And as you can see, it is also not linear. All right, so on the next page, we have, well, next 2 pages are some handouts that show different cross-section shapes with certain items defined in there. So you can see you got the cross-sectional area, the moment of inertia about the z-axis, which is the bending axis, capital R, right, which is the distance to the centroidal axis from the center of curvature. And then this term here, the integral of dA over lowercase r, which we haven't encountered yet, but we will shortly. So this is something you'll definitely want to find in this handout when you encounter problems in your homework, right? You've got it showing up for different cross-section shapes here. Where is it? Yeah, there. So we'll talk about that more in a moment. Before we move on from this, I just want to point out that a few other things that you'll want to remember, all right? These can come in handy. So in your homework, which I haven't picked out yet or haven't assigned yet, but you'll have some kind of cross-section shape that will be applicable, or at least applicable enough to one of these options. All right, so in the past, sometimes I've given a T shape. So it would be applicable to this option. You would just set either T1 or T2 equal to TW, right, or something like that. So this B distance, lowercase b, is always going to represent the distance from the unloaded center of curvature to the closest fiber, the closest edge of the cross-section. And then lowercase a will be the distance from the unloaded center of curvature to, in the radial direction, to the farthest edge of the material cross-section. All right, so those are 2 items that you'll be looking up in addition to that integral term. So we'll come back to that when we talk about homework, which will be next week, because I haven't pulled it together yet. So we still need to define Rn, right, which is the unloaded position of the neutral axis, and d theta d phi. So since we have no net axial force with bending, this has been a recurring theme for the last few lectures. I mean, it's always true, but we've been using it a lot, right? And that's, of course, for the case of pure bending. So I'll add pure to that line. We have the force Fx is equal to the integral over the area of normal stress in the x direction, and that's equal to 0, no net axial force. So we can say 0 is equal to integral over the area, sigma x dA, which is equal to, making our substitutions, capital E times d theta over d phi. So those are non-variable terms that we can pull out in front of the integral. And then within the integral, we have Rn over R minus 1 dA. And since Rn is not a variable, we can bring that out in front of the integral. So Rn times capital E d theta over d phi times the integral. Let's see. So this is actually going to expand a little bit. So now I'm going to have a square bracket and then a round bracket and then the integral over the area of dA over R. All right, so that's from this first term after bringing Rn out front. And then to account for the second term, we will have the area divided by Rn. That is equal to 0. Since we know that these are not equal to 0, that means this portion has to be equal to 0. So we can solve for Rn as the area of the cross-section divided by the integral over the area of dA over R. Now this term in the denominator, right, this is that term that I pointed out in the handout. So we would want to evaluate this. So I'm going to make two notes tied to that denominator. We need to evaluate that integral to determine the neutral axis radius. Which is Rn. And second note I'm going to make here is for a rectangular cross-section, that evaluation is t times the natural log of RB over RA. So that's lowercase r evaluated at the lowercase b distance, which takes you to the closest edge of the cross-section. And then in the denominator, you have that a value, right? So in terms of what was showing up in that handout, that would be, right, that would be your RB and that would be your RA, the way I wrote it in the equation. All right.
From the center, loaded
Before it's loaded, yeah. So we can make a note here that this line represents the center of curvature before loading. In this handout. All right, and you can if you forget that or you don't have this note, right, you can come back to that conclusion based on the definitions of capital R, right, which is shown here, and the so mainly on that, right. So capital R is always measured from the center before loading. All right, where are we here? All right, so we're out of time, so we'll stop here. But any questions so far? All right. I know, this lecture is packed. It's probably one of the more complex lectures and topics in this class, actually. So we'll finish it up on Monday. Yeah. All right.